So today's lab is about open channel flow, and as I said, it's a very important topic as a civil engineer. In this lab, we are going to know how we can apply Manning equation to describe the open channel flow. And at the end of this lab, we will also talk about a very important concept that is called critical flow. The equipment that we are going to use today is called teaching recirculating flume. It is something that looks exactly like this. It's a longitudinal channel that consists of main components. The first component is give me one second. The first component is this part at your left. This is a water tank that has a submerged pump in it, which suck water from the tank and pass it through several tubes up to this point here. Then the water will start to flow within this rectangular channel. The second component is the screw jack. This is a very important component here that we can use to adjust the elevation of this point. So if you can imagine, if this point is higher, this means that I am achieving a large slope. And if it's very low, this means that the slope is very low. So the main purpose of using this screw jack is to change the channel slope. The section of this channel is rectangular, and the dimensions of this section is listed here. So this is the cross-sectional shape of the channel. It has a 76 millimeter wide and 250 millimeters tall. So this is the overall dimensions. And the length of this channel is 5 meters. Great, so there is nothing more than that I said here. The slope can be adjusted using the screw, and it is also listing the tank and the pump. So before getting further into the experiment itself, let's speak a little bit about Manning equation. I'm sure that Dr. Abukifa has already introduced Manning equation in the lecture, so I will pass through it very quick. Manning equation is originally derived to describe the uniform flow, and it assumes two main assumptions. The first one is that the flow is uniform, and also the flow is steady. And I mean by uniform flow is that the slope of the water surface is parallel to the slope of the channel bottom. So in case if this is the flume that we have, and for a certain flow rate, this is the water level or the water surface, we can classify this flow as uniform in case the slope of this line that represents the water surface is parallel to the slope of the bottom of the channel. And steady flow is the flow that has a constant flow rate. The flow rate does not change with time. In this case, we can classify the flow as steady. Otherwise, you won't be able to use Manning equation. You have to use a different equations. It's also showing here that Manning equation was derived using a force balance approach. And the force balance was done to two main forces, the gravity and the friction force. The gravity force is what is causing the flow to move, what is causing the water to flow within the channel, and what is actually resisting the water from moving is the friction. So just imagine that there is a fluid passing through this channel because the point give me one second. because this point here, point 1, is higher than the end of this channel. There is a slope, and this is why the water have to or has to move or has to flow within the channel. On the opposite side, this cross section is made from certain material that has a friction with the flow. So if this friction is very high, the water won't be able to move as quick as if this friction is very low, right? So these are the two types of forces that acting on the water inside this flume. Getting back to Manning equation, if we are using the SI units, Manning equation can be written in this form. It's a simple representation of how the water velocity or the flow velocity is calculated based on other parameters. These parameters are N, which is the Manning roughness coefficient, R, which is the hydraulic radius, and finally S naught, which is the channel slope. So it's easy to know the physical meaning behind the channel slope. It's something that you can sense. It's also physical meaning to sense the velocity. But what about the Manning coefficient and hydraulic radius? So let's start by Manning coefficient. Manning coefficient is a representation of the roughness of the cross section. And I mean by the roughness is the resistance. How does this cross section resist the water flow from moving? So I will give you a very simple example here. So just imagine that we have a cross section that is made from glass. These three sides are made from glass, and there is another section so let's draw this with a different color, and this other section is made from wood. So we have a wooden section and a glass section here. So which section do you think will have a more resistance to the flow moving inside? Which section is more rough? Which section will exert more friction force on the water particles? The wood, of course, because here the glass is very, very smooth, so it will allow water to flow very easily, while the wood will have a more resistance. So this is why we use this parameter, because it represents the roughness of the section, and accordingly it also related to the material of the section. Great, so what about the hydraulic radius? Actually, hydraulic radius does not have an easy physical meaning, so I can explain for you. But it's a ratio between two other physical things. The first one is the cross-sectional area and the water perimeter. As you can see from this equation, R equals the area of the cross-section divided by the water perimeter. The area is something very common, and for a rectangular cross-section, for example, the area will be the width of the section multiplied by the depth. So, for example, if this is the water level, this distance will equal to y, whereas the width of this section will equal to b. Okay, what about the water perimeter? Actually, the name implies the meaning of itself. It's the water perimeter. In other words, it's the length or the distance that has an interaction between the water itself and the section. So for this section here, this is the distance of water perimeter. This is the length of the water perimeter. So how can I calculate the water perimeter in this case? It will be very easy because I can say that the water perimeter equals the width of this section, the bottom width, plus twice the water depth, right? Because there is a side on the left and a side on the right. Questions? Easy, yeah? Great. So knowing that Manning equation is very simple, you just calculate these variables and plug it into the equation, and you can get the velocity within the flume or within the channel. It's also worth mentioning that in case if you are using English units, and this will be the usual thing here in the US, you will have to use a different version of this equation. The constant or the coefficient 1 in this equation will have to be replaced with 1.49, and of course the length scale will be in feet, but the same variables will stay. There is nothing else will change. Up to this point, everything is clear and we are just dealing with the equation as it is. So let's dive into the advantages of this equation. Why actually I am using, or why actually we need to use Manning equation in open channel flow simulation. Because if you are going to design any open channel, and this open channel can be as simple as our flume inside our lab here, or even more critical and more complicated one, like if you usually go to the downtown to like walk beside the river itself is actually an open channel. It's a man-made rectangular cross-section that has the water flowing inside. So this is the actual practice or the practical use of open channel. The designer of this open channel used Manning equation to be able to decide the elevation of the sidewalks, the elevation of the rail, so people does not fall inside. And if there is anything that increase the flow rate, this will cause flooding. So the designer will have to make a certain kind of factor of safety. So getting back to open channel and Manning equation, the main purpose of using Manning equation is to compute something called the normal flow depth. And the easy description of the normal flow depth is the actual flowing depth at a certain flow rate. So instead of using a meter or maybe like using a stick to measure the flow in the old fashion, if you know the parameters of the flow, you can easily get the flow depth. So I can get the flow depth using equation number 3, but you might think that equation number 3 is different than equation number 1, but this is not true. Equation number 3 is exactly the same, but in a different representation. Why is that? Because to derive equation number 3, we can easily multiply equation number 1 by Q, because equation number 1 states the relation between the velocity and the other parameters, but most cases I use the discharge in this application. So I can say that the discharge equals the area multiplied by the velocity. So I will multiply equation number 3 by the area. So it will be A 1 over n r to the power 2 over 3, and then the square root of S naught. So if you try to simplify this equation further, you can do a very simple trick. You can put everything, I'm sorry, this is U, not Q. You can put everything that is related to the cross-sectional properties in one side, and everything that is related to the flow characteristics on the other side. And that's why it kept the AR on the left-hand side and Q S naught on the right-hand side. After doing this, it will be very easy for you to get the value of the water depth. But someone might say, okay, where is exactly? I can't see any y in this equation, right? So do you know where is the y? Where does the y lie here in this equation? Exactly, it's inside the area and inside the hydraulic radius actually, because the area is function of the cross-sectional parameters b and y in case of rectangular section, and also r is a function of p and y. So we will see at the end of this lab how we can even simplify this equation further than this. There's nothing new here, but it is giving you like a reminder that the flow shouldn't or doesn't always follow Manning equation. In some cases, in some open channels, we can't apply Manning equation to get the normal flow depth or even the flow velocity. Why is that? Because at the beginning of this lab, we mentioned that there are two main assumptions for Manning equation. It is assuming that the flow is uniform and the flow is steady. So in case if you have a non-uniform flow or a non-steady flow or unsteady flow, you can't use Manning equation. So what are the cases that the flow become non-uniform? There are several cases actually, but for example, if you have a control structure within your channel, and as an example for these control structures, something called weaves or sluice gates. The weaves, we are going to get into that in a while, but we are not going to do the same for the sluice gates, but you can search for it. It's a very interesting structure that is usually built within the open channel so it can control the water level and the flow discharges. Or also in case if you have a change of the water depth, of the water width. So just imagine that you have an open channel with 5 feet width, then for whatever reason it had to contract to 3 feet. So in this case, this is a non-uniform flow. You can't apply Manning equation. So at this point, we have almost finished the first objective of this lab, which is introducing Manning equation and understand how it can be applied to get the normal flow depth. So do you have any questions? Okay, after this, the main concept is the critical flow. In general, there are several categories for uniform flow. In this lab and like most probably you won't deal with non-uniform flow unless you do something in practical, but every course you will take and study in your undergraduate courses, it will be dealing with uniform flow. So uniform flow has 3 subcategories. A uniform flow can be critical, it can also be subcritical or supercritical. We won't talk about sub and super, but I think Dr. Bukefa already did in the lecture. In this lab, we are going to focus on critical flow. And what makes critical flow very special is that the specific energy is minimum in the critical flow situation. So you might think, okay, what's important or what's unique about specific energy? If you use this equation, which represents the specific energy, and somehow did some manipulation, you will be able to derive another equation or another dimensionless number that is called Froude number. And Froude number is a ratio between inertia and gravity forces. So if you reach a situation when Froude number was equal to 1, this means that you are actually dealing with critical flow. Critical flow has several advantages and several disadvantages. We are not going to like mention them here, but the main advantage of critical flow is that we can use this approach in a very useful way, and this way is to calculate the flow rate over the wheels. Wheels is a very simple tool that can be inserted within the channel itself to give you an estimation of the flow that is passing through the channel. So instead of using Manning equation and having to like measure the slope, measure the Manning coefficient, and also measure the water depth, you can only use this very simple equation to get the Q. So let's see the parameters inside this equation. Here it says that B is the width of the wheel. Of course, this is like a 3D structure. It has 3 dimensions. This is the width, the dimension that is not appearing in this image, the width perpendicular to the picture itself. And it has also the upstream head, H, this parameter here. And H is simply the distance or the depth of the water just above the crest of the wheel. N is an exponent, which is simply, in case if you are dealing with a rectangular cross section, will equal to 1.5. So these are the 2 main parameters or the 2 main characteristics for any wheel. But actually we left the C parameter. But it's not something new. You already faced this parameter before in lab number 5, if you remember. If you remember the discharge coefficients that we had to calculate for the different discharge meters, that accounts for the difference between the actual and the theoretical or the calculated flow. Do you remember this? So it's the same thing. C is called the discharge coefficient that accounts for the difference between the measured and the theoretical flow. And what is good about wheels is that in case if you determine the discharge coefficient for the wheel, it will stay the same even if you used it to measure the flow in a different channel. So just imagine that we have a certain wheel and we would like to calibrate this wheel. So we can use it in our flow. Then we can use this wheel to measure the flow within any similar channels. I haven't to calculate the discharge coefficient again. Great, so before getting into the procedures, do you have any question regarding the wheel equation and why you are using wheels and hydraulics and fluid mechanics? Great, so the experiment procedures are very simple. We are just going to repeat the same steps because in this experiment we are going to do 4 trials. The first trial will be for 1% slope, so you will use the screw jack to set the slope to 1%. After doing this, of course, you will have to turn on the pump and open the control valve to allow the water to pass through the channel. Of course, you will have to record the mean flow rate. And if you remember in lab number 5, we used something called the displacement meter to get the flow rate. Do you remember this? It was a very long time ago, I understand, but it was something that we used to get an estimation of the actual flow inside the channel. Because any equation that you are using is giving something called the theoretical flow rate. It's something that is only valid in physics. It might not be 100% true. So to compare the theoretical to actual flow rate, you will have to get the exact flow rate. In this case, you are going to use a different tool that is called the calibrated basin along with a stopwatch. So the main idea here, before going any further, is The flow rate, the discharge, is a simple relation between the volume of the water and the time it takes water to pass with a certain volume. Like just imagine that you have a very large tank and you would like to fill this tank with water. So if you know the volume of this tank and if you know the time this tank needs to be filled, you can divide these two values to get the discharge rate, right? So what does the calibrated basin in our case is it gives you an estimation for the volume in liters. So to get the flow rate, you will have to use the stopwatch to check the time it takes between the initial and the final position, and this will be in seconds. So the overall units after doing this would be liters per second. But if you saw the worksheet, you will see that the units is meter cubed per second. So you will have to convert from liter per second to meter per second. And to do that, you should do one of these two things. You can divide by 1000 or multiply by 10 to the power negative 3. Okay, so this is the third step. We are going to record the mean flow rate, and of course we will have to record the water depth because this is a very important variable within our calculations. And up to this point, you have finished the first trial in the first experiment. So as I said, we will do 4 trials. This is one of them. Okay, what will be the second trial? The only difference is that you are going to use the screw jack and change the slope to 1.5% and repeat the same steps again. Okay, so these are 2 trials. The same 2 trials will be repeated but for a different bed material. What I mean by bed material, if you remember, we mentioned that the bed material of our flume is metal. So just to understand how Manning coefficient changes with changing the bed material, we are going to exactly do this thing. We are going to change the bed material. So to do this, we are going to use a rough surface. Yeah, here. We are going to insert a rough bottom tiles and do the same procedures again 2 times, so it will be 4 tiles in total. After doing this, you will be done with the first experiment. Then the easy part comes here, and the real experiment will start by removing the rough bottom inlays because you will conduct the experiment on the smooth surface. You will attach the broad crested wheel and you will set the slope to 1.5%. Then you will repeat the previous steps. You will repeat the step of recording the mean flow rate, then the step of recording the depth. Great, so at this moment you already know every theoretical part of this experiment. So that's why I'm going to head to the worksheet to make sure that you got the idea. Here it asks you to list the channel width. You already know this. It's 0.076 meters. It's something that was given in the lab instruction manual. And these 4 values are measurements. Because in each trial you will have to measure the flow rate and the flow depth. Whereas this part will be a very simple calculations. Area will be the depth multiplied by the width. The velocity equals the discharge by the cross-sectional area. B is the weighted parameter. We already talked about this. And R is the ratio between A and P. So you won't use Manning equation up to this point. To solve this column or to get the calculation of the corresponding n, the corresponding Manning coefficient, here you will have to use Manning equation. How? Manning equation says that the velocity, in this case, it is v equals to 1 over n a r to the power, I'm sorry, there is no a here, square root of s naught. So at this point, you actually know everything in this equation unless n, right? Because you have calculated the velocity, you have calculated the r naught, and s naught is already given. You can easily get the Manning coefficient for the first experiment and for the second one. So the question here will be, do you think that Manning coefficient will change by changing the slope? Because the only difference between the first and the second experiment within the experiment layout is the slope, right? I didn't change the bed material. I didn't like change the bump. I didn't do anything. I just changed the slope and took the measurements. So do you think the Manning coefficient will change by changing the slope? Yeah, I can see some saying no. Actually, if you focused on the first the Manning equation, it looks like n is independent of s naught, right? Because velocity is dependent on these parameters, but actually n is not dependent of s naught. It's a different variable. It is independent. So if you are dealing with an ideal situation, the first Manning coefficient should be exactly the same as the second Manning coefficient, right? But actually this is not our situation. This is not the case that we are dealing with. So in our case, the first n will be different than the second n. And there is a reason for this. So can anyone explain this for me? Knowing that the cross-section that we are using is composed of two different materials. This would be the situation if we are dealing with a cross-section that is made from one material. Like if the sides and the bottom were made from glass, this would be the case. N will be the same. But since we are dealing with a composite section, N won't be the same. But the reason now is why. The question now is why this will happen. Yep.
So when you increase the slope, the velocity profile is going to change. It's not going to stay the same. So it could be this can affect the end because the end is like more uniform, right? So this is going to be changed when you increase the slope, increase the velocity. So the profile.
Actually, what you are saying is very, very close to the correct answer, but it's not exactly the correct answer. Why? Because like changing the slope will change the velocity. This is something that is totally true. But n does not depend on velocity. Actually, velocity depends on n. Because n only depends on the cross-section material, the sides. And it affects velocity, but it's not vice versa. But what you said is true because changing the velocity will change the water depth. And changing the water depth will change the contribution of each component of the cross-sectional material. So if you understood this from the first time, this is fine. If you didn't, I will repeat this very slowly. So what you what your friend has just said is that if this is the cross section and this is the bed that is different than the other two sides, and in case of the first scenario, one where S node was equal to 0.01, the water depth will equal to a certain y. Let's say it's y1. Okay? Increasing the slope to 0.015, what will happen for the flow velocity? It will increase, right? Because based on Manning equation, velocity has a direct relation with S. So increasing S will increase the velocity. So by increasing the velocity, what will happen for the flow depth? Do you think it will go up or down? So should y2 be in this position or in this position? Which position is true? The dotted line or the continuous line? Increasing the velocity will reduce the cross-sectional area, right? Reducing the cross-sectional area has two things to do. It can either reduce the width or the depth, but it can't reduce the width. The water can't say, okay, I will only pass through this width only. This is like an open section. This can't be happen. So the only thing left is that the cross-sectional area will be reduced by reducing the water depth. So this will be the water depth in the second scenario. Any questions up to this point? This is the easy part. Okay? So how does this affect the Manning coefficient? If you think about this as each side contribution in the total Manning coefficient, you will see that for the first scenario, the Manning coefficient, let's say total or equivalent or whatever, was due to two things. The first one is the contribution from the metal bed and the glassy sides, right? So what is the length or what is the distance that water interacts with metal for the first scenario? If this is the width B, what's the distance or what is the length that the water interacts with the metal bed? It's B, right? So it's B. What about the sides? 2y. So the glass sides 2y. But in the other scenario, the end total comes from the same two materials. It comes from metal bed that has the same length B, and in this scenario the glass sides will have a different distance. It will be 2 1 y2. So changing the contribution of each side will actually affect the end total. No one can say that end total for the second scenario will be the same as the first scenario. Why? Because here we already know that y1 is larger than y2. So the contribution of the glass in the first scenario is higher than the contribution of the glass in the second scenario. Okay? So knowing this, which Manning will be higher? Which section will be more rough, in your opinion? Is it the first scenario or the second one? If I am trying to represent the section roughness as a whole, which section will be more rough? The second section, the second scenario, or the first scenario? So I will make this question easier. Which material is smoother? Is it glass or metal? It's glass. So knowing that in the first scenario, the glass contribution is higher than the second scenario, this means that the first scenario has a more smooth surface than the second scenario, because the contribution of the glass here is more than the contribution of the glass here. Okay? And actually, this is the answer for the second question, because it asks you to calculate the average Manning coefficient after doing the two trials, and it asks you, why does Manning coefficient change by changing the bit slope? And this whole story is the answer of this question. Great. So the rough bit calculations and measurements will be the same. You will only get a different values for Manning, of course, and it will be higher because you are using a more rough bit. And then for the real experiment, it's a very easy experiment, because here it asks you to write down the real height. The height that we are going to use is 10 centimeters in height, 0.1 meters. And the width is exactly the same as the channel, it's 0.076 meters. Then you will have to measure the flow rate and write it down here. This is the measured flow rate, the depth upstream the weave. Then you will have to calculate the upstream head. And the upstream head is very easy to calculate, because it will be the depth minus 0.1. 0.1 is the real height. Because if you remember, in this schematic here, the h variable or the h parameter was the distance or the depth up to the crest of the weave. It's not the overall depth. It's not this value. Yes, then it asks you to get the discharge coefficient. So what is the discharge coefficient? Again, it's a coefficient that takes into account the difference between the measured and the calculated flow. So in this case, the real equation says that Q equals C B H. In our case, the power is 1.5. If you have the Q, C, and H, you can easily get the value of C, right? Because this will be the only unknown in this equation. And you will write down the discharge coefficient. And after doing this, you will be done from the first, the second, and the fourth question.
So the age is the same, the upstream.
Sorry?
So the age value is the same.
The N?
The age, the height is the same, like depth upstream.
The depth upstream was calculated based on the depth upstream. Like, again, like let's go back to the schematic view. This is the depth upstream. This is the depth upstream. This is the value that we measure. And this is the height of the weave, which is 0.1 meters. So to get the head upstream, you will subtract 0.1 from the depth upstream. So the only question that is left here is question number 3, and actually this is the main objective of this experiment. or in general Manning equation, is to calculate the normal flow depth. So in this question, it asks you to use the average Manning coefficient that you have just calculated in the previous question, and to consider the smooth bed condition, and consider the slope to be 0.01 to get the normal flow depth. For two different flow rates, the first one is 0.005 and the second is 0.015. So how can I calculate the normal flow depth? So let's go back to the equation number 3 and write it down here so we can see how we can solve question number 3. It's a r to the power 2/3, then the water characteristics or the flow characteristics, n q divided by s to the power half. Everything on the right hand side is already known. Why? Because we already know the Manning coefficient. We calculated this. The q for the first example or the first question is 0.005. S is already given as 0.001. So I can simply calculate this term. Can you do this for me, please, and tell me the answer? If you have a calculator. Should be 5 multiplied by 10 to the power of something. 0.005. Yeah, 3 zeros 5, right? So it's 5 multiplied by 10 to the power negative 4. Okay? So it's more scientific and professional way, by the way, to use the scientific approach to represent your numbers. Even it will be easier for you to write it in the calculator. So try to use it as much as you can. So okay, what about the left hand side? And actually, this is the main concern here, because we said before that the area is a function. The area and the hydraulic radius are a function of p and y. So I will have to write down this side as a function of y. So for the area, it is equal to by, and in our case the width is equal to 0.076 y, and this corresponds to the area, whereas the hydraulic radius is equal to the area, the same thing, divided by the width parameter, which is 0.076 plus 2y, and this will equal to 510 to the power negative 4. So what's special about this equation that I am giving it this much of concern? What's the difference between this equation here that only has one unknown, that is y here, and the Manning equation that I told you, okay, solve Manning equation and get n? What makes this equation unique? Can you see any difference? Can you see any difference? Of course, I mean by difference in the type of the variable, not the numbers itself. So the main difference is that this equation is very, compared to the previous one, of course, it's very hard to solve. Why? Because y here is an implicit variable, whereas n in the previous equation was explicit. You can put in one side and the other variables on the other side, use your calculator, n equals something. But here you can't do that. You can't say y equals something. Even if you try to do this at home, you won't be able to do this. Why? Because there is y in every term, and it won't be easy to separate it from the equation. So to solve this equation, you will have to follow a trial and error approach. In trial and error approach, what you are actually doing is you assume a certain value for the y, you check your assumption, you compare two results, and if the two results are equal, this means that your assumption is true. So let's do this. Here I will assume different values for y. I will check the left-hand side of this equation, and the right-hand side, in our case, will be constant. It won't change, right? We have already calculated the right-hand side, and it is equal to 5 multiplied by 10 to the power negative 4. So let's say that I have assumed y and it was equal to, I assumed y to be 0.1 meter, of course. Then after calculating the left-hand side that is represented by these two terms here, I found that it is equal to 4 multiplied by 10 to the power negative 4. So is my assumption correct? No, it's not correct. Why? Because the equilibrium is not achieved yet. The left-hand side does not equal the right-hand side. So what I have to do is to change my assumption. So what if I tried 0.2? Let's say that in this case, the left-hand side is equal to 6 multiplied by 10 to the power negative 4. This means that the correct value for the water depth lies in between 0.1 and 0.2. So let's test 0.18. Let's say that this was 4.89 multiplied to the 10 to the power negative 4. This is very, very close to the right-hand side. Then I can say, okay, the correct value or the correct answer for y is 0.18. Okay? Have you ever dealt with the trial and error approach before? You did, right? Great. So this shouldn't be something new, but this is how we get the normal flow depth in case if we are dealing with a rectangular section. And I think this is it for the theoretical part, and we will have to we'll have to do the experiment right now. But there's something I would like to let you know about, and it's very useful regarding the trial and error approach, and this might save you some time, not only about code, but this might also be very good in other courses as well. So would you mind if I changed the style of this equation to a different style that looks like this? 0.076y multiplied by 0.076y over, I forgot to put the power here, divided by 0.076 plus 2y to the same power minus 5 multiplied by 10 to the power negative 4 equals 0. Do you mind if I did that? It's the same thing, right? Actually, this equation, you can solve it using your calculation, using your calculator, without even having to spend time of trial and doing this calculations many times. How can I do this? So I will turn on the camera. And again, this is not something you can do only in this course. This is something general that you can make use uh, in any other courses. So in case if you have, and I'm sure that most of you have a different models from this Casio calculator, and this Casio calculator has a very efficient tool called table, and you can access the table by pressing the setup, then 7. Once you press 7, it asks you to let it know the function, the f of x. In our case, it's an f of y, right? But changing x to y to z to whatever letter won't make any difference. So if you want the calculator to do this trial and error on your behalf, you only have to write down this equation here. How? It's 0 point, so let's use the brackets, 0.076. Then I would like to write the variable. I want to insert the variable. To do that, you will press the alpha x. So this is the first term. I will continue doing this. 0.076 s 0.076 plus 2x to the power 2 over 3 minus 5 multiplied by 10 to the power negative 4. After writing the equation, you just need to press equal. And because it actually does the same trial and error that you do, it needs a start and end points. So what is the lower value for y? Y can start from 0, so I will press 0 for the start. I will press the equal sign. It asks you for the end. When should I end calculation? Of course, if you like inserted 100, it will take forever to produce the table, right? So you have to be smart. This is a very small flow, so that the flow will be between like 0 and maybe like 10 centimeters, which is 0.1. So I will say that the end is 0.1 equal. It asks you about the step. Like, do you want me to do this calculation each 0.05, 0.02? So you do this, you select. I say, okay, 0.01. And what is actually doing right now is giving you the results directly of the 0, or the the right hand side. So the correct answer will be when the f of x is exactly equal to what? No, not 5 times 10 to the power 0. Because actually I have moved this term within the equation itself, right? So you will search for the position where the 0 lies. Here we don't have any zeros, but we can say that the 0 lies between. Do you see that screen clearly, or you don't see it? Can you turn off the lights, please? Can you turn off the lights? It's worse now, or is it clear? So as you can see here, the value of x, which corresponds to the value of y, and the corresponding value of fx, which actually the value of the right hand side. So the correct value should be at the position where the f of x equals to 0. But actually I can't see zeros here. But of course 0 is in between these two numbers. Why? Because the sign of these numbers change. So I can do a more accurate result. I can say, okay, now I know that the correct answer lies between 0.7 and 0.8. So I will press equal again. I'm sorry, I will press AC. I won't have to rewrite the equation. I will just press equal. When it asks me about the start, I will say, okay, it's 0.07. When it asks me about the end, I will say it's 0.08. When it asks me about the step, I will say it's 0.001. And see, here you can see that there is a very, very small number. It's 6.2 to the power multiplied by 10 to the power negative 6, which is actually 0, right? And this is the answer. This is the actual normal flow depth. It's 7.7 centimeters. So do you think this tool is helpful and it will save time, right? It might not save that time here because the calculations is very simple, but I can assure you that in several situations you will be facing a very hard time doing the trial and error. Great, so now we are done with the theoretical part and we are going to do the experiment, but I will turn off the recorder.